First, a little bit of background and introduction. IMA, the goals, or I should say benefits of IMA are lower swap, size, weight, and power, better portability, easing integration, easing certification, and it's based on this idea of modularity, whereas formerly you might have had different software functions running on different LRUs, separated computing platforms, so they are federated. In an IMA system, you're bringing all those software functions together into a single computing platform, which is enabled by the higher power, higher performance processors we have today. But now the separation between those software functions needs to be provided through some sort of isolation or partitioning mechanisms, and those are typically implemented in both the hardware and potentially in a software layer such as a hypervisor or RTOS. I've got a list there of a number of the relevant standards that apply in this situation. DO-297 is sort of the base document that describes this IMA approach and describes what the different stakeholders are in developing such a system. ARINC 653 describes a partitioning environment that helps implement that isolation. You've heard from multiple speakers today on CAS 32A, which is the FAA position paper, and you maybe saw a reference to this upcoming advisory circular. 20-193 will be formalizing the guidance in CAS 32A, harmonizing it between FAA and EASA, and there is actually a draft that is out now on 20-193, and it will be expected to go to actually get published in its final version probably sometime early next year. And then ARINC 664 is more on the I/O side on communication in a partitioned environment. Partitioning works both in terms of isolating time, isolating space or resources, if you will, and potentially bandwidth, doing both. And then we'll be talking a little bit more about this idea of the partitioning platform, which I'm going to use to refer to both the processing hardware and any partitioning environment in RTOS or hypervisor. And then compared to that, these individual functions that get partitioned we'll call hosted partitions now. So you may be familiar with that like under a virtual machine sort of model if you're using a hypervisor where there's applications are hosted within those virtual machines. You can do ARINC 653 without a hypervisor per se. Either way, you're going to have this idea of partitions. So what is the problem that we're discussing here in this presentation? It's how to do certification of such complex systems where you've got multiple software functions, perhaps at different levels of criticality, all residing on the same system. And so what we'd like to achieve is a way to do this incrementally, where you can generate assurance, that is certification artifacts, for the different applications, the different partitions individually and independently, and then accumulate that evidence over time rather than having to do everything all at the same time. So this applies sort of both to your baseline development of a product, and if you ever in the future add additional hosted applications. So in the first time fielding that product, we'd like to be able to develop the underlying platform and then separately develop each of the individual software partitions and assure them independently of the other ones. Especially these may be coming from different suppliers and coming together and being integrated by yet another company. So it is very helpful if you can do this incrementally. In addition, we'd like to be able to add new partitions in the future. If we've set aside or provided some spare slots, we'd like to drop an application in there in the future and not have to go back and recertify the existing applications that were certified under the original product release. So this incremental approach is helpful for when we might add something in the future as well. Our proposed solution is you've seen hints of in the previous presentations, is to use an interference generator. Rapita brands these as Rapidemons. They're a form of an interference generator that creates stress on a multi-core interference channel. And I'm going to walk through some of the means of verification, some of the steps of verification, and some of our tools. So first on the means. Three concepts here I want to just briefly describe. We use instrumentation, that is we're creating probes within the software to see what's happening. So this instrumentation, which is very lightweight, gives us a view of what's happening inside the software. You heard my colleague Sam also mention we even have a zero product where you can do this with the appropriate hardware without inserting anything in the software itself. But in some way you need a view, some way to insert these instruments in the software to see what's happening. And the interference generator, as you heard, is for us a rapid daemon that's creating stress on a particular interference channel, and we want to see what that effect is. And so we're going to take measurements based on that instrumentation to see what is the impact of that interference. So our steps are to first look at the partitioning platform by itself. So this, as I mentioned, is the hardware and potentially a partitioning environment, an RTOS or a hypervisor. And we're going to then separately and independently, incrementally, look at each of the applications, each of the hosted partitions, doing the assurance of that. And then throughout this process, we're accumulating that evidence to create the overall package. So first on the platform, we want to show that the hardware, that computing, the processor hardware, plus the RTOS, it's some sort of partitioning environment, probably enabling an ARINC 653 schedule, ARINC 653 sorts of API. That combination sufficiently is isolating the hosted applications. What we're looking for is that the impact of one partition on another, we'd like to ideally be zero, but in practical terms, we have to show it's bounded, that it's deterministic, that we can measure it, and that it is never more than a certain amount. And then in the end, we need to show that each of the applications and each of their partitions is meeting the requirements, even in the face of this interference coming from the other partitions. So hopefully it's very small, ideally zero. Our goal practically is to measure it and be able to bound it to show that we can deterministically verify that the applications all are meeting their requirements. The partitioning that we're testing is building walls around the applications so that they're not impacted by each other, and those walls form in a couple different dimensions. You may partition resources. For example, you might have an application on one core. That core might have its own level 1 cache, as you've seen with some of the NXP processors that we've been reviewing in this conference. And another core might be running another partition, and it's got its own L1 cache. So those resources are partitioned. They each get their own. You might also be partitioning main memory. They each have their own area of memory. But there might be some that are shared, say a last level cache where the different cores are all sharing within that cache. So there's got to be some way to isolate that interaction as well. So you might use time partitioning where you give different time slices to different applications. And you may do a combination of time and space, and you could think of that as, say, a bandwidth types of partitioning. And so some combinations of those mechanisms has to be implemented to isolate the different applications. Then we turn to assuring the applications themselves. We want to make sure that the resources allocated to that application are sufficient. So for example, did we allocate enough memory out of the total amount of memory that we have available to allocate? Did we allocate enough time on a core so it can get its tasks done, even in the worst case? So our goal here is that we can individually assure through testing, through verification, that the application is meeting its requirements and is receiving its allocation of resources. As you'll see in a moment, and as you heard in Sam's presentation, our rapid daemons are generating a high amount of interference to a particular channel, and this gives us the ability then to estimate what the worst case is. Now you might think, well, wouldn't you rather just put the actual other applications you're anticipating in those other partitions, because maybe they don't create as much interference as your rapid daemon? Well, that would prevent you from doing this incremental acceptance. The goal here is that no actual application that you add today or in the future will ever create more interference than the rapid daemon. Since you test against the rapid daemon, you won't have to retest in the future. You know you already threw the worst thing you can at your application, and if it survived that, if it was isolated sufficiently from that, then nothing you might do in the future in those other partitions could be worse than that. So that's why we want to do this worst case approach. So let's think of an example. Let's say you're building a reasonably complex system using an ARINC-653 partitioning environment on, say, a 4-core processor, and you have, let's say, 6 independent applications. So those are going to be mapped to partitions, and in this case, they're mapped to a time slot. So the ARINC-653 major frame is repeated over time, as shown here. And then you have minor frames, which are those kind of smaller vertical bars there that separate that major frame up. And then that just gets, that fixed schedule gets repeated. So I've got my 6 partitions allocated to a particular minor frame on a particular core. Partition 4 represents a partition that might be multi-threaded, so it's going to use all 4 cores within its minor time frame. Other partitions are just on 1 core, and then independent partitions on some of the other cores in their same time slot. And then I have a few spare slots that we may want to use in the future. So our incremental approach to doing this is first to characterize the platform. We're going to run a Rapidemon on each core within a particular minor time frame. And so we're testing Rapidemon against Rapidemon. That is, what's the worst I can do to a particular shared resource where this interference generator is just focusing its energy, creating all the bandwidth it can on that particular interference channel. That gives me sort of an outer bound on what might happen, what's the worst impact that might happen, helps us to get a handle on what's the overall characterization of the platform. The platform provider generally is going to do this task, possibly working with someone like Rapita to characterize that. And then each of the partitions are being hosting an application. So each of those suppliers needs to say, well, what happened to my application? So now we run that particular application on its assigned core within its assigned minor time frame. And any remaining cores are going to now have a Rapidemon creating this interference. These have been tuned and calibrated based on that previous step. So we now know we're throwing the highest amount of interference we can. And we're going to see what happens to that particular partition when we do that. Does it still meet its requirements? We do this then for each of the applications at one at a time, putting Rapidemons in the other cores as we go. And eventually, you accumulate this across all of the possibilities. So we're running all of the different applications one at a time by themselves. This could be done in parallel, each being verified independently. All those artifacts then get collected together into the overall certification package. The DO-297 describes this incremental approach and describes how the certification authority can provide incremental acceptance. So you can work with the certification authority at each of these steps saying, here's what we did on this partition, and they can give some indication, yes, this is looking good, keep going. That's not the final approval, of course, but it does give you that incremental progress towards the overall certification package. So then let's turn to some of the tools that we can use in doing this work. You've heard about several of them already in the previous presentation. I did want to emphasize first the fact that we do this measurement on target. There are verification tools that work through static analysis, work sort of in a host development environment. Our tools specifically are measuring on the target, and that's important. I want to read this quote from CAS 32A. Quote, since interference between applications occurs via the proprietary internal mechanisms of an MCP, a multi-core processor, any simulation of those mechanisms is less likely to be representative in terms of functionality or execution time than testing conducted on the target MCP, end quote. So that's right from CAS 32A. The multi-core processors are complex enough that it's just impossible to get a static model that's going to capture all the nuances of the interconnect in the processor, how that is interacting with how the RTOS is managing it, and so forth. So your best bet for measuring the actual interference is to do the measurement on the real system, on the target. And then preferably you're integrated with the RTOS so that you're getting some visibility and insight into how the RTOS is configuring and managing the underlying hardware. So you've heard about these tools, so I don't have to go into detail here, but we typically for this kind of testing are using our Rapid tool for managing the unit and system tests, the RapidTime tool for gathering that data. So that's the tool that's going to gather the instrumentation data and allow us to estimate worst case execution time. The interference generators, which we call RapidDemons, these are these tuned pieces of software that are going to run on the other cores and intentionally create interference. And then we put this together in a CAS 32 compliance package that is available that we use as a service working with our customers to do these sorts of measurement. I should mention that if you're doing a system this complex with mixed criticality software, if you have either level A or level B software in the system anywhere, then you're looking at needing to do much of that verification with independence. So it is important that these tools are easily run by either, say, Rapita as a service or by a separate team of engineers doing verification where you can track and have a paper trail demonstrating that independence of verification. All right, and so an example, looking at the platform characterization, software characterization, and a few sample results. So for this example, we looked at the NXP LS1048A. We were running the DDCI DOS operating system using their ARINC 653 scheduler. And then we looked at some specific examples of interference generators. So earlier I described this RapidDemon as if it was a single thing, but now I need to tell you a little more detail. It's actually a whole set or catalog of RapidDemons because you need one that's tuned for each of the particular shared resources you might target. So for this example, we had one targeted at the L2 cache, which is the lowest level shared cache in this particular processor, and at the DDR main memory. And then you can see there's actually nuances within that. So you could have more than one interference channel based on different modes of usage of a shared resource. So we had a reader and a writer for the L2 cache interference generators. And then for the DDR memory, we actually had three, a reader, a writer, and then one that did a combination because we had some information that that you could actually see a impact of a interleaving of reads and writes to DDR memory depending on how what the pattern of addresses was. So those were the RapidDemons in this particular pilot project we used to exercise the shared resources. Just real quickly, for those of you not familiar with the LS1048A, it's actually very similar to the 1088A, just has 4 cores rather than the 8. So I've just shaded out those other 4 cores of the 1088. All the rest are the same between the two variants. So you've got 4 ARM Cortex-A53 cores. They each have their own private L1 cache. It's a split cache between data and instruction. That set of 4 core shares an L2 cache. It's a unified cache. And then everything else below there is also shared. You can see in the upper right there the DDR memory controller. So the cores are going to have to go through their caches, assuming that you would have misses on the caches. You're now going out to main memory. Across the interconnect, it's the CCI 400 coherency fabric in this case, through the memory controller to get out to that memory to get their data. And similarly for any other I/O that you might be accessing in the system, there's going to be the potential for interference because those are shared resources. So that was the hardware we're looking at. We were running the DOS RTOS on top of that, and then we said, okay, what happens when we just compete RapidDemon against RapidDemon? So we're not putting an application in place here, just seeing what's sort of the outer bound of what could happen if we have intensive activity just to a particular resource. So here's what happens when we hammer the L2 cache, and this is when we're hammering it with writes. Let me explain the graph here a moment. The vertical axis is the execution time for a single run of the test, so higher is more time there. And then the horizontal axis is the individual execution run. So you can see I ran 800 tests here. Every 200 iterations, I added a RapidDemon. So on the far left, the first 200 are a rapid daemon without any competition on the other cores, and so we get sort of a baseline timing. And you can see the staircase effect. Every time I add a rapid daemon, the time of the original rapid daemon, the baseline case, goes up. It experiences interaction and interference from the other rapid daemons until I've saturated when I have all 4 cores running a rapid daemon, and you can see on the far right the highest amount of time there. So the time is increasing considerably here, but this is an outer bound. It's just rapid daemons competing against themselves. We'll look at the application in a moment. One other view of that data that I think can be helpful is this probability distribution. So this is the same data, but now the vertical axis is the frequency that we saw the particular execution time, which is now the horizontal axis. And you can see 4 very distinct distributions here. On the left is the baseline case where it was 1 rapid daemon without any interference, no competition. And then as I add adversaries, you can see a very distinct distribution moving to the right until you see on the far right where all 4 were running. What this shows me is that there is an impact from interference, but it is predictable. It is, I can determine it. I can estimate a worst case execution time, but I am seeing that there's a performance impact, at least for this particular shared resource. Again, this is not an application characterization yet. So let's add that in. We looked at 2 applications, a matrix multiply and a Mandelbrot image generator. The Mandelbrot image generator was quite CPU intensive. The matrix multiply actually was doing a fair amount of memory reading and writing. If you remember your high school algebra, matrix multiply means you've got to read from 2 matrices, multiply them together, moving across rows and columns, and then writing out to the destination matrix, the answer. So you're doing quite a bit of reading and writing with just a little bit of computation on each of them. So this gave me sort of 2 ends of the spectrum, from very CPU intensive to rather memory intensive. So here's a sample result. This is that probability distribution again, with frequency as the vertical axis, execution time as the horizontal axis, where it goes higher execution time to the right. So first, the red distributions. You can see 4 reasonably distinct peaks there as we added different rapid daemons. These happen to be doing L2 cache reading. And then you heard Mike describing earlier the DOS approach to cache partitioning. When we turn that on, what you see is that you get a tighter probability distribution. That is, it's more predictable, so we've got better determinism and actually better performance in this case. The worst case you can see is not as far to the right. So there was definitely some benefit from using that cache partitioning in this case. So I wanted to spend a fair amount of time on several things that we saw from this little pilot project and talk about where we're going next. So this is my last slide. If you did have questions that my colleague Sam was not able to answer on the question forum, feel free to pop those in. We'll get back to you, or you can email me. I've got my email at the bottom of the slide, and these will be posted on the MCFA SharePoint as well. So let me walk through a couple of things that we saw in doing this pilot project. So first of all, one way to think about interference is what are the usable number of cores? If you were originally on a single core system and now you're considering moving to, say, a 4-core system, can you expect that you can run 4 times as much? Can I drop 4 equivalent applications in the system compared to the 1? Well, if they're CPU intensive, similar to that Mandelbrot image generator, yeah, you almost can. We saw that you get nearly 4 times the performance on 4 cores versus 1, and it's deterministic. You can verify it. You get almost 4. Not quite. There is a little bit you have to deal with for margins, but not quite. For memory intensive applications, we saw that it's less so. That depending on how you configure this, there's a lot of variation here, but in one example we saw that 4 cores you could get roughly 3 cores of reliable performance. You need to leave some margin because of the interference, but you could bound that, and you could see that it was deterministic within those bounds. So you could say get 3 cores. I have in there or less because it does depend on the applications, the particular shared resources that those applications use. But we did see examples where, yeah, you get good improvement. The reason that it drops in part is because you're doing a trade-off. To get better determinism, often you're going to have to trade off performance. That's not always the case. You saw in that L2 read graph I gave earlier that you actually get both. But we saw, for example, L2 cache writing, that there appeared to be a bottleneck. It was either a capacity issue or a write port issue, and we couldn't tease that out further just in our pilot. But we could get to a point where we could generate enough interference that it was difficult to squeeze out more performance. You would lose determinism. So definitely that trade-off is there. Any engineer knows that that's going to be the case in most systems, and we definitely saw that here. And so there are things you could do to accommodate that. You might need a bigger cache, so you might have to move to a different processor that has a larger cache, or use a different form of that partitioning that we were using on DOS, or optimize the way the applications are using it. So lots of ways to approach that, but definitely needs to be verified and assured. We are seeing, with working with a variety of customers and looking at where the industry overall is going, that there's some consensus forming on how you do this verification. And it is centered around interference generators. And we're not the only ones doing this. There are other folks that I see are attending this conference and have published some of their approaches as well. And so we know that we, as well as others that are part of this group, are using some form of interference generator to do this verification. We happen to call ours Rapidemons, but the underlying approach is that you must stress the interference channel and measure the impact on your application to ensure that you've mitigated it sufficiently. And again, ideally, there's no impact, but realistically, there's some. And the job of the interference generator and the verification tools is to ensure that that's bounded, quantified, and hopefully allowing you to do this incremental approach. So those are some of the things that we learned in this pilot project. I did want to also mention where we're going from here. So the future work includes looking at DO-297 and just applying this incremental acceptance in a way that gains industry-wide acceptance. So we're proposing that this seems to make sense of the way to bring DO-297 forward. It was written in the time of unicores. How do we apply that in the multi-core world? How do you mesh that with the advice of CAS32A? So working through that, working with a number of our customers who have really challenged us exactly on this point, how do you do this incrementally, is something that is ongoing. And so what I presented here is really a start to that, but we hope to work with many of you on continuing to work this out. Secondly, identifying significant interference channels. How do you do that when you have a very complex processor? Some of the processors we saw during this conference had not just a few interference channels, but dozens or even hundreds of them. So how do you do that in a cost-effective way? How do you perform that analysis, which is part human engineering analysis? You can't completely automate it and ensure that you've done it completely to the satisfaction of your cert authority. So how do we do that effectively and efficiently? In a related point, this third bullet is how do you characterize interactions between interference channels? In this pilot example and the example Sam gave in his presentation, we were just doing one interference channel at a time. There's the potential that you might see a different effect if more than one channel is being stressed at the same time. So how do you look at those combinations appropriately? And of course, how do you handle what's potentially an explosion in the number of test cases? And how do you manage that effectively to provide assurance, clear evidence that the system is safe in the presence of all of these potential interference channels that might even be interacting with one another? And then lastly, maybe related to the first future work bullet, is working out what are the commercial structures for doing this incremental acceptance. So there's not just the technical approach of how do you put together these artifacts, but how do you enable companies to work together where you might have a system integrator that is a separate company from the platform provider, which is a separate company from each of the software application providers. So it's a complex situation between many different suppliers that need to work together smoothly to create the overall certification package. Because as you know, it's the overall system, the entire aircraft that's certified, not the individual pieces. So although we're doing incremental acceptance of these individual components, in the end, all of those components need to be, that evidence needs to be accumulated into a single certification for the aircraft. So looking at how do we enable companies to work smoothly together where they're each protecting their own IP, they each need to interact with one another to ensure that requirements are being allocated and met, and then in the face of all of this, ensuring that those requirements are met with the potential for multi-core interference. So technically and commercially, we see there's additional work to be done here that we are in conversation with our customers, and we invite others in this forum to be talking with us, and we hope to have further conversations in future MCFAs about how do we work this out to enable these different parties to work together effectively. So I'm going to stop there. I see that Sam has been able to answer a few of the questions. So I see one is the platform partitioning assurance only necessary for the IMA platform provider. The way that we envision it is that you would first look at the platform by itself, and that gives you the ability to fine-tune the RapiDemons, identify which shared resources need to be tested and verified, but you're not done there. Now you go to each of the application providers with that platform plus your RapiDemon measurements in place and test the impact on their particular application. So you're ensuring that the requirements that they've been allocated, so for example, can they get their tasks done within their minor time frame? So they've been allocated a certain amount of time. Are they finishing, even with some margin for worst case, within that appropriate time and accomplishing their requirements? Now adding multi-core interference, do they still meet those requirements? So it is a sequential process there, but then once you're to the point of verifying application providers, you could do those in parallel. You could work with each of them separately. They each have their own verification test that they need to do. And if you've done it right, it can be done incrementally. That means each of them don't depend on each other. They do depend on the platform, but they don't need to see each other's results to be able to do their verification.